Okay, so this is the final video in our parabolas topic, and what we want to look at here is intersections between lines and parabolas. So looking at finding the coordinates of the points where a line and a parabola intersect. And obviously this can, we'll just look at the process of this, but this can clearly have applications where, you know, the parabola might represent a certain quantity, I don't know, cost of a taxi journey or whatever it might be, and a line represents something else, and where they intersect is an important point in terms of the context. But we also want to think about this more generally in terms of a sort of geometric problem. So first of all, we want to think about the three different ways that a line and a parabola can intersect. So obviously a straight line and a parabola could cross at 2 points, and this would be an example of where that's happening. So, you know, they meet at 2 points, and we see this happening when we talk about x-intercepts as well. A parabola can have two x-intercepts because essentially the x-intercepts are where a line meets with a parabola, so they can cross twice. Okay, they can also just cross once, and that's where the line is what we call a tangent to the parabola. So it just caresses the side of the parabola. So they just touch each other at that point. They don't actually, the line doesn't actually cross through the parabola. They just touch at this point here, and the line stays completely below the parabola. And that happens, we've seen that happen with x-intercepts, where we can have a parabola with just one x-intercept where the turning point sits just neatly on the x-axis. And again, you know, an x-intercept is an example of where a parabola meets with a straight line. It's also possible to have no points of intersection between a line and a parabola, and that's where the line could sit completely completely below, or completely above the parabola. So obviously if we had a sad parabola, we could have a line that passes completely above it and they never intersect at all. And again, we see this happening in the context of x-intercepts when the parabola sits completely above the x-axis or when it sits completely below the x-axis. So there's three possibilities. We could get 2 points of intersection, 1 point of intersection, and that is when the line is tangent to the parabola, or no points of intersection. Okay, so let's have a look at just the algebra of how we would go about finding the points of intersection, and then we'll come back to that idea of the number of points of intersection. So first example here is to find the coordinates of the points of intersection between the line y equals 4x plus 5 and y equals the parabola y equals x squared plus 3x minus 1. So it should have also said, you'll recall that when we're finding the points of intersection between two graphs, we find that by solving the equations simultaneously. And when we solve two linear equations simultaneously, we have a number of different solution options, elimination and substitution. When one is a line and one is a parabola, substitution is always going to be the way to go. And usually substituting the linear graph into the linear equation into the quadratic equation is less complicated than doing it the other way around. So for example, here in example 1, we know that 4x plus 5 is equal to y. We can substitute that in place of y in the other equation. Okay, and so we get that 4x plus 5 is equal to x squared plus 3x minus 1. Okay, so we have a quadratic equation to solve. So the first thing we want to do is get everything on the one side, make one side 0. So let's subtract 4x and subtract 5 from both sides. So we'll get x squared minus x minus 6 equal to 0. Solving a quadratic equation, if we can solve it by rearrangement, we will. We can't in this instance because there's more than one x term that are not like terms. Then we look to see if we can factorise. Factors of -6 that add up to -1. Yes, we'll be able to do that. Okay, so again, remembering, I know there's some of you still persisting with the more complicated factorisation method. That's only needed for non-monic quadratics. So if you have something other than 1 here, yes, you'll need to do this number times -6 and split the middle term and factorise by grouping. If there is only 1 here, you do not need any of that, and you can just write your answer straight down. So our two numbers go straight into the brackets. Factors of -6 that add up to -1 are -3 and +2, and immediately we've factorised. Simple quadratics should be one line factorisation process. Okay, now we're using the null factor law. If these two things multiply together to equal 0, the null factor law tells me that either this thing, x minus 3, is equal to 0, or this thing, x plus 2, is equal to 0, and from that we get that x equals 3 or x equals -2. Okay, so what we've done here is we've found the x coordinates of the points where the parabola and the line intersect. So we're seeing that there's 2 points of intersection. Okay, so for example, we've got parabola and a line. We're seeing the x coordinate of this point is -2, and we're seeing the x coordinate of this point is 3. Now the question asks us for the coordinates, so we want to know what the y values are. So when x equals 3, what does y equal? When x equals -2, what does y equal? Now we can substitute these values of x into either equation, but again, it's always going to be easier to work with the linear equation. You only need to put subbing x equals 3 into this is easier than putting it into this. Okay, both will give you the same value. That's the whole point. They intersect at these x value, and so therefore they have the same y value at this x value. So, but you want to make life easy for yourself. So if x equals 3, this means that y will equal 4 times 3 plus 5. So that's 12 plus 5, which is 17. If x is equal to -2, y will equal 4 times -2 plus 5. So that's -8 plus 5, which is -3. And so therefore we have 2 points of intersection, 3, 17, and -2, -3. Okay, let's have a look at another one. Find the point or points of intersection between the line with the equation 2y minus x equals 16 and the parabola y equals x squared plus 3x minus 2. Okay, so this time you've got the equation of the line written in a slightly less standard form. Okay, so you haven't got x or y as the subject here, so it's harder to substitute the linear equation into another equation. Remember, substitution works best when at least one equation has x or y as the subject, and we have that in the quadratic equation. So we know that this here is equal to y, so if we take that and replace y in the other equation with that, we'll have a single equation involving x. So we're going to have 2 times -x squared plus 3x minus 2, so that's our substitution. Take away x equals -16. And so then we need to focus on solving this quadratic equation. So let's expand out the bracket, -2x squared plus 3x minus, sorry, I forgot the times 2, plus 6x minus 4 minus x, and let's add the 16 as well while we're here. Okay, let's collect like terms. -2x squared plus 5x minus 4 and plus 16 is plus 12. Okay, it's always harder to factorise when the x squared term is negative, so let's multiply everything by -1. So 2x squared minus 5x minus 12 equals 0. Okay, no common factors. Can't be solved by rearrangement, so we're looking to see if we can factorise. 2 times -12 is -24. Factors of -24 that add up to -5, yes, they'll be -8 and +3. So we rewrite the middle term using -8 and +3. So minus 8x plus 3x is the same as minus 5x. We've still got 2x squared and minus 12. Then we factorise by grouping. So 2x is a common factor, x minus 4, plus we factor out 3 times x minus 4, x minus 4 times 2x plus 3. And so null factor law tells us that either x minus 4 equals 0, which means x equals 4, or that 2x plus 3 equals 0, which means 2x equals -3, or x equals -3 on 2. Okay, so that's the x coordinates of our turning point. Sorry, not turning points. The x coordinates of our points of intersection. And so we then need to find the y coordinates. Again, we've got two options here. We can take these and we can substitute them into the quadratic equation. The advantage of doing that is y is already the subject, but you are going to have to put x in two places and square it, and you've got a fraction that you have to then square and add, and potentially that's more complicated. Or you put them into the linear equation, and in this equation y isn't the subject, but potentially the rearrangement isn't too difficult. Both present issues, so I don't mind which one you choose. I might go with the linear equation. Okay, so sorry, I should have left just a little more room here. So when x equals 4, we know that 2y minus 4 is equal to minus 16. So adding 4, that's 2y equals minus 12. So y is minus 6. And when x is negative 3 on 2, 2y minus 3 on 2, so plus 3 on 2 equals negative 16. Let's multiply everything by 2 to get rid of those fractions. So that's 4y plus 3 equals negative 32. So subtracting 3 is negative 35, and y is negative 35 on 4. Okay, so therefore our 2 points of intersection, 4, negative 6, and negative 3 on 2, negative 35 on 4. So again, that parabola and that line intersect at 2 points. Okay, I'm sorry. Now, example 3 is determine the number of points of intersection between these two graphs. Now, it's not asking us to actually find the points of intersection, it's asking us to find how many points of intersection there are. So, you'll recall that when we want to know how many solutions a quadratic equation has, we use something called the discriminant, and that's going to be useful to us here if all we want to know is the number of solutions rather than what the solutions actually are. So if we want to find the points of intersection, we would need to solve an equation where we've combined these two using substitution. So if we take 5 minus 2x and sub it into the quadratic equation, solving 5 minus 2x equal to 2x squared minus 3x plus 8 would give the points of intersection. Let's make one side 0. So 2x squared adding 2x gives negative x, taking away 5 gives 3. Okay. So the solutions to this equation are going to give the points of intersection. Now if we want to know how many points of intersection there are, we can consider the discriminant of this particular equation, because the discriminant of this equation will tell us how many solutions the equation has. Okay, so the discriminant, remember, is b squared minus 4ac, doesn't involve the square root, it's a common error. So b is negative 1, so it's negative 1 squared minus 4 times 2 times 3. So that is 1 minus 8 times 3 is 24, so it's negative 23. Now when the discriminant's negative, remember our quadratic equation says that the solutions to the equation are negative b plus or minus the square root of the discriminant over 2a. So if your discriminant, this bit in under here, is negative, you can't take the square root of a negative and there are no solutions. Okay, and so since the discriminant is less than 0, so since it's negative, the equation 2x squared minus x plus 3 equals 0 has no solutions. Hence, the line and the parabola have no points of intersection. Okay, so thinking about how the discriminant can help you to determine the number of points of intersection, we would have found, even if we tried to find the points of intersection, we would have first attempted to factorise. 2 times 3 is 6, factors of 6 that add up to negative 1. Factors of positive 6 that add up to negative 1 don't exist, and so therefore it wouldn't factorise. Then we'd try to use the quadratic formula, and in doing that we'd discover that the discriminant's negative, and so there's no solutions. But if the question's just asking you about the number of solutions, just focus on the discriminant first, and then you can determine the number of solutions just from that without actually fully solving the equation. Okay, and that's where we lead into an example like example 4, where we're really forced to use and understand the discriminant. So here we want to find the value of k such that the line with the equation y equals x plus 1 is tangent to the parabola with equation y equals x squared plus 2x plus k. Okay, so is tangent to tells us that the line and the parabola must intersect once. Okay, that's what we need to happen. Alright, so let's think about how we would go about finding the points of intersection. So again, to find the points of intersection, we would try and solve again. We'd substitute that's equal to y. Let's replace y in the other equation with that. So we get x plus 1 equals x squared plus 2x plus k. We then get everything on the one side. I'm going to keep that x squared term positive, so let's subtract from the left-hand side. So subtracting x, we're going to get plus x, and subtracting 1, we get plus k minus 1. Okay, so if they need to intersect once, that means that we need the discriminant of this equation to be equal to 0, because that will make sure that that equation has one solution, and therefore the line and the parabola intersect at just one point. Okay, so let's focus on finding the discriminant. So remember, the discriminant is b squared, b is 1, minus 4 times a, which is 1, and times c, which in this case is that. Okay, so I'm just using a slightly different colour. So that's c, that's b, and that's a in this quadratic. Okay, so b squared minus 4 times a times c, that's my discriminant. And so that is 1 minus 4 lots of k minus 1, which is 1 minus 4k plus 4, and so it's 5 minus 4k, okay? And so we need discriminant to equal 0, which means that 5 minus 4k has to equal 0, so 4k has to equal 5, and therefore k has to equal 5 on 4. So if k was to be equal to 5 on 4, then that parabola and that line would just intersect at the one point. Let's have a quick look at those graphs just to confirm that. So if I draw in the line y equals x plus 1, so that's already fixed. Alright, and then if I draw in the parabola y equals, sorry, not y equals, x squared, that's what the f2 of x is for, x squared plus 2x plus, now I'm going to make it something other than 5 on 4, so if I make it something bigger than 5 on 4, so let's say I make it 2, okay, so when k is 2, we can see that the parabola and the line don't intersect at all, okay. Let's make k something smaller than 5 on 4, so let's make it 1 or 0, for example. So if I change k, let's just make it 0, we see that in that instant the parabola and the line intersect at 2 points. But if we were to make k 5 on 4, we hope, as we found, that that's the value that will make sure that the parabola and the line just intersect once. And you can see there that that line is tangent to the parabola. We're just getting that one point of intersection. It doesn't ask you where the point of intersection is, this question. It asks you to find the value of k. So remembering, focusing on what the question's asking you for. Find the value of k, therefore my final answer should be k equals something. You know, previous question here, determine the number of points of intersection, no points of intersection. Okay, no ambiguity about answering the question. Find the points of intersection, points of intersection. Okay, find the coordinates of the points of intersection, coordinates of the points of intersection. Okay, so making sure you answer the question at all times. That's the most common thing I write on VCE tests and exams. Answer the question. Answer the question. It's really simple, but lots of people don't do it. A couple of other things just in terms of finding points of intersection using your CAS. Let's just have a couple of chats about the different ways that we can do that. Let me just go back to perhaps the first example to use as an example here. So I'm just going to press delete 3 times. Okay, let's start again. So you could do it graphically. I would not advocate doing it graphically. This is going to be the most time-consuming way. But we could draw our two graphs, y equals 4x plus 5, and y equals x squared plus 3x, plus 3x minus 1. Okay, you're going to play around with your window a bit to get it so you can actually kind of see what's happening a bit better. Particularly, we need to make that bigger, probably bigger than that, sorry. Let's maybe make that 20, see how we go. Yep, there we go. That bit smaller. Okay, so we can see, might even make that bigger. Okay, so we can see what's happening here. Back to there so I can see the full parabola shape. Okay, so you don't need to play around with it as much as this, As long as you can see what's happening, that's fine. Okay, so we can clearly see there's 2 points of intersection. Now we can use our CAS in the graphing screen, so menu 6, 4 for intersection. And then we need this lower bound and upper bound thing. So we move this horizontal dotted line so that it is somewhere to the left of the point of intersection, and then somewhere to the right. Now you can only do one point of intersection at a time, so we do this process for that first point of intersection, which is at 2, -3, and then we repeat menu 6, 4 for the second point of intersection, somewhere to the left and somewhere to the right, 3, 17. Okay, now this works beautifully for this example because we've got nice whole numbered points of intersection. Now, what if I changed, let me just change my parabola, for example. Let me make that x squared plus 3x minus 2. I don't know if this will work, but let me just see if that happens. Yeah. Okay, so now what we see all of a sudden is that the points where that line and that parabola intersect, they're not whole number values. And our CAS only works with decimals. So if the answers are whole numbers, there's no problem with working, the graphing screen if you're CAS. There's no problem with working in the graphing screen if the answers are whole numbers. But you don't know if the answers are going to be whole numbers before you find them, okay? It wouldn't be correct if the question said find the coordinates of the points of intersection between these two, this parabola and this line. It wouldn't be correct to give those answers as decimals unless the question explicitly said give your answers to 2 decimal places or whatever it might be. And in that case, we'd still need to be careful here because you'll notice here that this 17.8 is not to 2 decimal places. So we would need to click on that number, do a right click, which on your handheld is pressing Control menu, choose Attributes, and see more digits of the number. So at the moment we're only seeing 3 digits, 1, 7 and 8, but that's not giving me 2 decimal places, so I see some more digits, so then I can actually give that answer to 2 decimal places. It's very fiddly, very time consuming, and very rarely will you be asked to give the points as decimals anyway. So I wouldn't be encouraging you to find the points on the graphing screen. If however you've drawn your graphs first, fine. Then I would solve my equations over in the graphing screen, okay? So over in the graphing screen, you want to solve f1 of x, which is the first graph, the linear graph, equal to f2 of x, which is the parabola. Oops, sorry. We want to solve that for x, and then we've got the exact x coordinates of the points where they intersect, and then to find the y coordinates, we're going to substitute into one of the functions, it doesn't matter which one, and we can either retype in this expression, square root of 29 plus 1 over 2, or you can copy it down, but it's a bit more complicated when the answer is given in this form because I don't want to, if I press enter it'll copy that whole thing. You can obviously do that and delete the bits of it that you don't want. Okay, which is that. So that gives me my y coordinate. So one of my points is root 29 plus 1 over 2, and the y coordinate is 2 root 29 plus 7. And the other point, again I'm just going to edit this because the only thing that's actually different is that it's minus root 29. If you expand out that bracket up there on the first line, you get negative root 29 and positive 1, so it's still plus 1. And so the y coordinate of that point is 7 minus 2 root 29. So you can get them exactly. Okay. If you hadn't drawn the graphs first, you could just type in that equation. So menu 3.1, I'll go back to my original equations on the paper here. We could just type in the equation we want to solve 4x plus 5 equal to x squared plus 3x minus 1 for x. We get the two values, and again then you'd need to substitute them in. So if you've defined your functions, the substituting back in is quick and easy. If we defined f of x and g of x and then solved f of x equal to g of x, we could then substitute back in more quickly, but here we're going to have to type it out ourselves. 4 times negative 2 plus 5 and 4 times 3 plus 5 for our two y values. That's pretty straightforward in this instance because the equations are pretty simple. But as I said, you could instead define your functions first. Define f of x as 4x plus 5. Menu 1.1 for define. Define g of x as x squared plus 3x minus 1. And then solving f of x equal to g of x for x. And then quicker and easier to sub back in, f of negative 2 is negative 3 and f of 3 is 17. And there's your 2 points again. Okay. last option would be to get your CAS to solve the simultaneous equations, so menu 371. Although usually the substitution's easy enough to do yourself, and then you can just solve, then you can just solve a single equation by typing that equation in, rather than, typing in the simultaneous equations. But it's up to you. So you can solve the simultaneous equations. The two equations are y equals 4x plus 5, or y equals x squared plus 3x minus 1. The advantage of solving the simultaneous equations is it will solve for both x and y, so you'll get your x and y values. So x equals -2 and y equals -3. The and tells you that's one of the points, so -2, -3 is a point. Or x equals 3 and y equals 17, so 317 is the other point. So don't jumble up the x and y coordinates, it's really explicit about how they combine together. X equals -2 and y equals -3, that's a point. Or another solution is x equals 3 and y equals 17, that's a point. Okay, so lots of different ways that you can find points of intersection with your CAS. And it's important, what underpins that is you having a clear understanding of what's happening when you're finding points of intersection, that you're solving equations simultaneously, how you go about finding the y values again, that you're finding the points of intersection between two graphs. So this little box sort of outlines how you can solve them using the simultaneous equations, or how you can use your graph, or how you can use the function definitions once you've graphed them, or you can define the functions yourself in the calculator screen using menu 11. So I don't want you to get too bogged down in the CAS. In fact, in the work I've differentiated. I want you to do most of it by hand, and then you can do question 5A using your CAS, playing around with what's going to be the most efficient method to solve the simultaneous equations in that instance. Okay, so exercise 7G.